So my name's Dave Heisel. I'm from Cornell University, and I was also a CEDAR student not very long ago at all. It seems to be, I guess, prerequisite to have been a CEDAR student if you're going to work in this field. So everybody in the room has done the right thing, and you've all taken the right first step. And I'm going to be talking about Equatorial Aeronomy, which is one of the really the main topic of my dissertation. And I did most of my graduate work here. And this is a picture of the Hikamarka Radio Observatory. So it was one of the earliest incoherent scatter radar facilities that was built. It's 50 years old. It seemed like an old place when I started working there, but in fact, I just realized that half of its lifetime was spent was coincident with my career. So it's amazing how time flies. And it's a big 50 megahertz phased array radar that's located not very far from Lima, Peru. And it just happens to be situated very near the geomagnetic equator. And most of the data that I'm going to show today came from this facility. If you don't know, incoherent scatter radars are able to measure the state parameters in the upper atmosphere and the ionosphere, density, temperature, composition, drifts, by observing very faint scatter from thermal fluctuations in the medium. This radar operates at 50 megahertz. It's also very good at observing non-thermal fluctuations and waves, and I'll show you some pictures of that. And if as a consequence of anything you hear today or this week, you'd like to spend some time at Hikamarka, you can do that. You can definitely do that. And if you contact me or other people involved with the facility, you can go down and spend some time there, wherever you are in your graduate career, if you're an undergraduate or graduate, whether you're particularly interested in equatorial aeronomy or not. I just wanted to go through a really quick gallery of some of the things that are observed at the dip equator and not really in other places. And by the way, this particular radar can really observe things from the stratosphere all the way right through the plasmasphere, up to maybe 6,000 kilometers. And so there's a huge number of targets that we look at, and many of them are unique to equatorial latitudes. So I'm going to start down here in the mesosphere. And it turns out there are just enough electrons at altitudes 60, 70, 80 kilometers that you can use the radar to observe fluctuations in the neutral gas, in the neutral atmosphere. And these are fluctuations associated with waves and instabilities in the neutral atmosphere, in the mesosphere, caused by dynamical instabilities and convective instabilities. And there are rolls that are visible in here and so forth. And so we can use the radar to look at neutral fluctuations at these altitudes. If we move a little bit higher, this is sort of 80, 90, 100 kilometers, we start to get lots of backscatter from meteors. And we can see the trails due to meteors through specular reflection. We can see the heads, meteor heads. And we can also see these very peculiar, intense echoes that come from plasma instabilities in the trails of the meteors. And these are actually very useful for diagnosing other features like the neutral winds that push the trails around at these altitudes. And the equatorial latitude turns out to be very helpful for observing these. If we move up a little bit higher, this is sort of 95 to 125, 135 kilometers. We have echoes from the equatorial electric jet. This is a very strong current system with currents that are comparable to the kinds of currents that flow at auroral latitudes. So strong is the current that it destabilizes lots of plasma waves. Plasma waves are produced spontaneously at these altitudes, and we can scatter from them and learn something about the plasma physics in this altitude regime. If we move up a little bit higher, 130, 140 kilometers, we get another class of echoes that occur around twilight, and we do not know the source of these echoes. They're new. They haven't been around for very long. We presume they have something to do with plasma inhomogeneity that occurs at the solar terminator. But it's, in fact, it's a new discovery, and we really don't know much about them. So 50 years into the game, it turns out that there are very fundamental, very obvious phenomena to be discovered that we don't know very much about. In the similar vein, moving up to about 150 kilometers, we have these very attractive echoes that are sort of punctuated in time and in altitude and form sort of a necklace shape. We're not very good in this community with naming things sometimes, so we call these the 150-kilometer echoes. And it turns out we don't know what they're all about either. They're very faint. They're not much stronger than incoherent scatter, and it turns out that we don't yet know their origin either, although we've made some progress. Moving up a little bit, again, this is about 250 kilometers. At nighttime, we find we can get intense backscatter from extremely thin layers that we call bottom-type layers. They're 10, 20, 30 kilometers thick, and we think we do understand where these are coming from. And they turn out to be precursors for this. This is sort of the cause célèbre of the equatorial ionosphere. This phenomenon is known as equatorial spread-off. And what we have here is extremely strong plasma irregularities that are driven by an instability, sort of a heavy fluid on top of a light fluid type instability that occurs at night. It's very frequent in the equatorial ionosphere. and it gives rise to these very, very startling-looking plumes that correspond to regions of depleted plasma pushing their way up through the peak of the F-region ionosphere and into the top side. And these cause all kinds of havoc with systems upon which humans depend, communications systems, navigation systems, imaging, things like star imagery, and trying to understand and predict what's going on here is one of the major foci of research in the equatorial zone. And I'll just say that these things can get very high. The last panel that I'm showing here shows some of these irregularities getting up to 2,000 kilometers altitude, which occurs very frequently during geomagnetically disturbed conditions, and it turns out very frequently after midnight. And that's sort of a new discovery, the fact that this occurs so late in the evening, right up through sunrise. So that's sort of a photo gallery of some of the things that one finds in the equatorial ionosphere and in not too many other places. So this is an outline of what I'm going to talk about. We've already done sort of the summary of some of the unique things that you see at the equatorial ionosphere. I'm not going to return to all of those topics. I just wanted to give you a sense for what's available. And what I'm going to do is I'm going to march through all of the things that people talk about when they talk about Aeronomy. And this is sort of everything there is to talk about. This talk is really emphasizing breadth over depth. There's not much depth here. I really just wanted to give you a flavor. I wanted to put a name to everything that you might hear about in equatorial Aeronomy. And later on, you can pursue the details of things that really interest you in particular. So to start out, I have to start out with the magnetic field. And if you write the magnetic field in terms of a scalar magnetic potential, you can develop from that what the magnetic induction looks like as a function of colatitude and range. And if you work on that a little bit, you can calculate the modulus of the magnetic field, of the magnetic induction. And it turns out that the magnetic field at the equator is about half as strong as it is at the poles. You can calculate the dip angle, the angle that the magnetic field makes with respect to a surface of constant altitude. And it turns out it's very handy. The tangent of the dip angle is essentially twice the tangent of magnetic latitude. And so what makes the equatorial ionosphere interesting is the fact that the dip angle is essentially zero. The magnetic field lines are essentially horizontal. And that's important. It turns out that if you have a bunch of charged particles on a common magnetic field line, in the absence of collisions, they will remain on a common magnetic field line. And that means that transport along field lines for charged particles is very, very easy. Transport transverse magnetic field lines is very, very hard. And so that sort of orders the plasma in the ionosphere. You can calculate a surface that is everywhere parallel to a magnetic field line, and it's given by this equation. It's ordered by this parameter L. Different L's put you on different magnetic field lines. And it turns out that all the particles on a magnetic field line in the absence of a collision stay on a so-called common L shell and are on a common flux tube. And we talk about volumes that are on a common L shell as being on a common flux tube. And we often analyze a flux tube independently and then let the flux tubes drift around. But the main thing is that the transport normal to field lines is difficult. Transport parallel to field lines is easy. So here's really a dramatic picture. What I'm showing is these lines are lines of constant dip angle. So here's the geomagnetic equator, zero dip angle. And I'm showing two different sets of curves here. The black curves were calculated for today, and the red curves were calculated for 1960, the time when the Higgs Observatory was built. And these curves are really, really different from one another. And so we think about the Earth's geomagnetic field as being sort of invariant, but in fact it evolves sort of on the length scale of a graduate dissertation. So here's Higgs over here. We're really fortunate that they built it on the west coast of South America and Peru. If they'd built it in Brazil at 1960, it wouldn't be an equatorial station anymore. It would be a mid-latitude station. And so the magnetic field is evolving incredibly rapidly. Also, what I want to point out is that on the previous slide, I gave you the equations for simple dipole magnetic field. But the Earth's magnetic field is very non-dipolar. It's strongly quadrupolar, in fact. And so in addition to the north and south poles that we're familiar with, there's also a sort of a secondary pole. One of them is over here in the South Atlantic, and another one is under Malaysia, it turns out, under Malaysia. And the secondary poles are actually growing in intensity even as the primary poles are getting weaker. So the fields are getting more and more non-dipolar all the time. But again, for our point of view, the interesting thing here is that at the equator, we've got field lines that are essentially horizontal. That means transport in the vertical direction is inhibited. The vertical direction is all important because the ionosphere is essentially vertically stratified. And if you can't transport things in the direction of the stratification, that means if you knock the ionosphere out of equilibrium, it's very, very hard to get it back to equilibrium. And that's really the characteristic that defines, or that makes the equatorial ionosphere unique. You knock it out of equilibrium, it's very hard to bring it back. So to begin with the beginning, I think people are familiar with the processes that determine ionospheric composition and plasma number density and so forth. And this is a continuity equation for plasma number density for some species. And these are transport terms that we'll come back to in a minute. And on the right-hand side, they're the terms that determine photochemical balance, production and loss. So ionization is produced by sunlight. And to have ionization occurring, you have to have some neutral species to ionize. And those are the terms sitting over here. You also have to have some irradiance penetrating down to that altitude level, and that's what's going on in these terms over here. And together you get a production function for some species driven by some wavelength of solar irradiance, and you have to sum over all species and over all wavelengths. And the point is this production function has a peak. Above some altitude, there aren't enough neutrals to ionize. Below some altitude, there's not enough radiation making it down, so this is a peak function. And then when you want to figure out what the number densities are, you have to solve some continuity equations for different species. And neglecting transport, here's one for the electrons, here's one for the ions. Ions are produced by this ionization term. This is atomic ions and electrons. You can also get molecular ions, and those are produced by charge exchange reactions from the atomic ions, and they're destroyed by dissociative recombination primarily. These are the main chemical pathways. And so when you put all this together, you get a coupled systems of equations, and you can solve it assuming an equilibrium configuration, solve for the electron density. And it turns out that if beta is small, if charge exchange is a limiting reaction, then you have this term balancing this one, and the number density is proportional to the production rate. And if beta is large and dissociative recombination is the limiting factor, then the electron number density is proportional to the square root of the production function. So this is a bit of an oversimplification, but it's essentially saying we expect the ionosphere to occur in layers. And indeed, that's true. And so here's a picture of the F layer over Hikamarka. And at least up to altitudes near the F peak, the F layer is essentially a Chaplin function, like I showed before. Transport terms start to be important near the F peak, but mostly things are in photochemical balance beneath that. But what's really interesting at the equatorial ionosphere, like I said, is the transport in the vertical direction is strongly inhibited by the horizontal field lines. This is what the F layer looks like during the day. Within a few minutes of sunsetting, suddenly the ionization sort of well below the F peak is destroyed. And the F peak becomes very, very sharply peaked. The gradient becomes very, very distinct and very sharp. The vertical density scale length down here is about 15 kilometers. This is an extremely sharp lower boundary for the ionization. And transport is not available to wipe that out. So we've pushed the ionosphere well away from equilibrium. There's lots and lots of free energy in the inhomogeneity that's present here. And it's not going to be, we're not going to be able to evaporate that or get rid of that through normal transport processes. And what that leaves is instability. It turns out that this steep gradient is very unstable, and it causes the whole ionosphere to become prone to the production of spontaneous waves and irregularities. And that's what spread F is all about. We'll see that in a minute. By the way, you can't observe incoherent scatter in the E layer over Hikamarka for reasons that we'll see in a minute. So when we want to learn about the E region ionosphere, we have to do it in other ways, and one way to do that is with rocket flights. Here's a sounding rocket flight showing what the E layer looks like during the day at low latitudes. And it's basically a Chapman layer, although it's very, very irregular in the bottom side during the day. For reasons that we'll see, it turns out that this gradient is also unstable and produces spontaneously plasma waves and plasma irregularities, and they're there every day. The nighttime equatorial E region ionosphere is virtually unexplored. Here we are, this late day in the game. We know almost nothing about it. I have to go back to 1972 to get a sounding rocket measurement of what the nighttime E region ionosphere looks like. And so far as we know, it's very irregular, and it's very sort of broken and choppy. These are not traditional standard sporadic E layers like you get at mid-latitudes. The processes that form mid-latitude sporadic E layers really are not very effective at the equatorial ionosphere. They can work, but they're not really a very dominant feature. And what we know about the nighttime E region ionization is it's extremely ratty, and we don't really know why. And so we don't have to search very far or very hard to find one of your frontier areas of investigation. We know almost nothing about this. It's virtually unexplored for historical reasons, and the fact that we can't do very much radar aeronomy at those altitudes. Let me go up to somewhat higher altitudes now. These are more Hikamarka data from 100 kilometers up to 1,600, 1,700 kilometers. We can actually make these measurements up to about 6,000 kilometers. But what I'm showing you is plasma number density. So here's the F peak during the day. This is electron and ion temperatures, electron in black, a little bit hotter than the ions in red. And this is constituency. We have O plus at these altitudes. This line is telling us the fraction of H plus of hydrogen, and the blue line is telling us the fraction of He plus helium. And so I want to discuss what's going on here in these topside altitudes, where now transport is nominally taken to be dominant over photochemistry. And so I'll talk a little bit about the temperatures and the energy balance, and I want to start off by talking about the composition and how it is that we go from O plus, an O plus dominated ionosphere to an H plus dominated ionosphere, and what helium is doing. H plus, by the way, is produced by charge exchange with O plus, and He plus is mainly just produced by photoionization. I'll tell you what the punchline is now, and then I'll explain it. It turns out that these curves that I'm showing you are incredibly variable. Even during quiet times, even during undisturbed times, from profile to profile, from day to day, these profiles are extremely variable, much more so than they would be at say, mid-latitudes. And the reason for that is, again, sort of this inability of transverse transport to sort of maintain equilibrium. So if we were working at mid-latitudes and we wanted to figure out what the composition of the topside ionosphere was, we could write down some force balance equations, say in the direction parallel to the magnetic field. And so we'd have pressure gradient forces and the electric field and gravity. And we could write them down for all the ion species we're interested in and the electrons. And the electron density has to equal the total of the ion density to maintain charge neutrality. And it turns out that you could solve this system of equations. And what you'd find is that all the species independently want to achieve hydrostatic balance. But they can't quite do it because the electrons have a much longer scale height than the ions. And so the electrons would like to go to very high altitudes and the ions to be concentrated at low altitudes. But that would violate charge neutrality. So what happens is a big ambipolar electric field forms. And that electric field pulls the electrons down. It pushes the ions up to keep them in their number densities balanced. And it pushes the light ions way up. So O plus hangs around at low altitudes. H plus is shot up to high altitudes, and helium gets squeezed in the middle. So these are some model runs showing that. So here's what H plus would look like. Here's what O plus would look like. And here's what He plus would look like. These are model runs, by the way, of Joe Huba's SAMI2 model. And this is the kind of thing that you would expect to find at mid-latitudes. Now, at low latitudes, how are things different? Well, the magnetic field is playing a role. The magnetic field does not appear in the Hamiltonian of the plasma, and that means the magnetic field should not be able to modify the equilibrium distribution of the plasma, and that's true. However, the presence of the magnetic field so slows down relaxation processes, so slows down transport in the vertical direction, that it means that, okay, the equilibrium configuration is the same at low and mid latitudes, but at low latitudes, if you're knocked out of equilibrium, you'll never get that. And these different curves that I'm showing here are different model runs where all we've done is modified the background electric field, the zonal electric field, and that pushes the ionosphere up and down, and it redistributes all these geomagnetic flux tubes. And so you can get endless variability, endless variation in how the constituents are distributed around. You can change the transition height quite a bit and push it up, push it down. You can change the shapes of these layers. The black curves here, by the way, are temperature. And it turns out that the same factors hold for temperature. If you start pushing flux tube up and down, you get adiabatic heating and cooling along these tubes. And the particles aren't really able to migrate away from the tubes to preserve equilibrium. So you can get huge variability in these curves at low latitudes that you don't get at mid latitudes. And that's something that we observe with Hikomarka. If we measure these profiles from hour to hour over the course of the day, we see these, the curves look like this for a while, they look like this for a little while, and they change drastically, even during quiet times. And that's just not something that's observed at other latitudes. Same kind of comments hold for thermal structure. The way heating occurs is photoionization comes along and transfers lots of energy to non-thermal electrons, to photoelectrons. The photoelectrons interact with thermal electrons and are thermalized through Coulomb collisions. The electrons interact with the ions through Coulomb collisions. The ions interact with the neutrals either by inducing dipole moments in the neutrals and colliding with them or by charge exchanging with them. You can also have electrons interacting directly with the neutrals through different kinds of inelastic collisional processes. And the point is the heat goes from the right to the left. So the photoelectrons are the hottest, then the thermal electrons, then the ions, and then the neutrals, and everything goes from left to right. Now, it turns out the temperature profiles that I showed you before can be recovered at the equator very easily. First of all, it turns out you can almost always assume quasi-equilibrium to throw out the time derivative terms in the heat balance equations. That's fine. And you can almost always just assume local heating and cooling. write down all of your heat sources, write down all the cooling sources, balance them, figure out what the electron temperatures are, the ion temperatures, the neutral temperatures. And the reason you can do that, again, is because the field lines are horizontal. That means that vertical heat transport is very small. It's very constricted. Horizontal heat transport by conduction, for instance, is perfectly viable, but who cares? It's a vertically stratified ionosphere, so horizontal transport doesn't do anything. And a direct transport by photoelectrons streaming along the magnetic field lines, likewise, the field lines are horizontal. The photoelectrons aren't going to get very far, and in a vertically stratified ionosphere, they're not going to do very much. So it turns out at equatorial latitudes, it's very easy to calculate electron and ion temperature profiles just by doing local heat balance calculations. With one counterexample, and the counterexample is sunrise. At sunrise, the ionosphere is so thin, the number densities are so small, that photoelectrons that are generated at both conjugate ionospheres, at the altitudes where photoionization is occurring most rapidly, can go right through the peak of the ionosphere at mid-latitudes, make it right up to the dip equator, and create lots and lots of local heating at low latitudes. And so the temperatures at sunrise just shoot up dramatically, and they go from being 600 or 800 kilometers to being 4,000 Kelvin, 5,000 Kelvin. So we have a situation where the electrons are trying to be cooled by the ions. At low altitudes, there aren't enough electrons and ions to take the heat away, so the heat resides with the electrons, and the temperatures are very, very high. At these altitudes, the ions are coupled pretty strongly to the neutral, so they remain cool, but as you go higher up, the ions are mainly coupled to the electrons, and so they get hot. So there's a period of about a half an hour where equilibrium is totally shot, where quasi-equilibrium assumptions fail, and where electron transport, photoelectron transport, becomes very, very important, and the temperatures sort of shoot off the scale like this. This phenomena, we're only now able to model this. We're only now really working very, very hard at coming up with numerical models that will reproduce this. It's a difficult problem, and it's only just now that we're able to sort of quantify this effect. Let me move away from dynamics to electrodynamics. What I'm showing here are the major species that make up the ionosphere, say, below the F peak. And over here, I'm showing the ratio of the collision frequency to the gyro frequency for electrons here and for ions here. And the point is that throughout the ionosphere, electrons are strongly magnetized. Ions, however, are only magnetized above altitudes of about 120 or 130 kilometers, and below that, they're very collisional. And that means the way that they respond to electric fields is very different above and below about 120 kilometers. And that gives rise to very, very strong electrical anisotropy in the behavior of the plasma. So we can write down a current density expression, and the conductivity is, in fact, a conductivity tensor because the medium is so strongly anisotropic. The Pedersen conductivity controls the current that flows in the direction of electric fields perpendicular to B. The direct conductivity controls the current that flows in the direction parallel to B. And then there's also a Hall conductivity, which controls the current that's flowing perpendicular to B and perpendicular to the electric field. So the whole thing is described by a tensor. It's very strongly anisotropic, and it's also very strongly inhomogeneous. And we have a kind of a difficult electrodynamics problem, but one that's very, very rich because things are so anisotropic here. The parallel conductivities are typically much bigger than the transverse conductivities, and the Hall conductivity is very large at some altitudes and small at others. Here's sort of some typical conductivity profiles. So here's the direct or the parallel conductivity. It's very, very high in the upper atmosphere. This is the Pedersen conductivity. Typically, it's fairly low. That's the transverse conductivity. This is the Hall conductivity, and it can be quite large. At some altitudes right around here, it can be much larger than the Pedersen conductivity at sort of E-layer altitudes. There's a fourth conductivity that describes the equatorial ionosphere called the Collin conductivity, and I'll come back to that in a minute. But the interesting thing is in the E region in particular, we have this really interesting situation where the conductivities are all very different. And from the Pedersen to the Hall to the Collin to the direct conductivity, it's a factor of 10, a factor of 10, a factor of 10, a factor of 10. So we have this tremendous dynamic range in the conductivities. Things are very anisotropic, they're very inhomogeneous, and the conditioning is just terrible because these numbers are so different from one another. You're thinking this is a terrible slide. Imagine how I feel. I have to describe it. What I'm going to do is in one or two slides give you the whole key to understanding electrodynamics in the equatorial ionosphere, and then we'll just look at a bunch of examples. But this is important. think about the picture up here. This picture is really meant to describe how a dielectric works. So now you have to think back to some of your introductory physics classes. In a dielectric, you have media with charges that are not entirely mobile, but they are free to shift from one side to the other of the molecule or the atom in question or whatever. And if you apply an electric field, you induce lots of little dipole moments. And the polarization is the dipole moment per unit volume. If the medium is inhomogeneous, like I'm trying to draw on over here, all these little dipole moments are such that in any small little neighborhood, you can find regions that appears to have excess charge in it, that appears to have net charge. Now, this isn't free charge. It's bound charge. But for all intents and purposes, it plays the role of charge. So over here, we've got associated with the gradient of the polarization, we have what appears to be some excess charge. Now, if you write down Poisson's equation just in a regular old dielectric, this bound charge appears on the right-hand side of Poisson's equation. It, for all intents and purposes, is charge. And the electric field that arises, say if you try to solve the electric field by looking at Poisson's equation, it has to be consistent both with whatever charge set up this electric field that began the whole problem, plus this induced bound charge that came about. And the electric field has to be self-consistent with all of it. That happens in a dielectric. That also happens in a low-frequency plasma. And if you like, you can think of the plasma as being made up of lots of charges that are being Debye shielded, and the Debye clouds migrate away from the charges that they are shielding, and that acts a little bit like a electrical dipole. The central equation that governs all of this is del.J equals 0. This is an equation that enforces quasi-neutrality. It's very expensive in a plasma to have real net charge build up any place, and so this equation prohibits that. If you enforce quasi-neutrality on the current density that I wrote down before, you can develop a complicated equation that looks like this. And it looks like Poisson's equation. On the left-hand side is del.E. This is E prime. This is E prime in the frame of reference of the neutrals. And that's how we can bring neutral forcing and neutral winds in to this whole expression. This is del.E equals everything on the right-hand side is playing the role of charge. And you see if you have electric fields in the vicinity of gradients in the Pedersen conductivity, or if you have electric fields in the vicinity of gradients in the direct conductivity, or if you have electric fields normal to gradients in the Hall conductivity, all of these things play the role of charge, of some kind of bound charge. They all play that role. And when you go to actually solve for the electric field has to be self-consistent with whatever set up the background electric field, and also with all of these sort of induced effective charge. That's basically the whole game in studying low-latitude electrodynamics. There are gradients in the conductivities, vertical, associated with the vertical stratification, but also horizontal, associated with the fact that the sunlight is distributed differently in different longitudes. And because of that, polarization electric fields pop up all over the place. And then the net electric field and the net circulation that accompanies it has to be consistent with all of this. So wherever you have gradients everywhere. You have irregularities in the way the circulation works. And let's see, I'll just point out that the parallel length scales are much, much longer than the perpendicular length scales because the parallel conductivity is so large. So all the structures that we see are very, very elongated along the magnetic field lines. And now what I want to do is just show some consequences of all of this. One thing that you can do is take that terrible equation that I showed before and assume that the magnetic field lines are equipotentials because the length scales are so long along them that the gradients and the potentials don't really develop. If you do that, you can actually integrate the equation that I showed you and solve, for instance, so here's a magnetic flux tube. You can actually solve, say, for the vertical electric field everywhere along this electric flux tube. And how does it come about? Well, if you have zonal winds, they will generate a vertical electric field by this expression. These integrals, by the way, are integrals along B. We talk about flux tube integrated quantities as being important. We think of sort of a quasi-two-dimensional system where we integrate out all the quantities along B because along B the potentials are constant. We can do that. So if you have zonal electric fields, they will give rise to zonal winds. They will give rise to vertical electric fields. If you have vertical winds where there's Hall conductivity, that will give rise to vertical electric fields. These are all mediated by the total conductivity along the tube. So we think about there being some kind of efficiency-limited dynamo process going on here. So winds are generating electric fields. That's the dynamo, but the efficiency is limited by the total content of the conductivity on the tube. If you have zonal electric fields and some Hall conductivity, that will give rise to a vertical electric field. And potentially a big one if the Hall conductivity is big, if it's bigger than the Pedersen conductivity. If you want to calculate the total zonal current density, some of that's driven by the zonal electric field that you began with, and some of that's driven by this vertical electric field that was generated by the zonal electric field that you began with. When we add this all together, the zonal current density is driven in accordance with the zonal electric field times all of this stuff put together, and we call that the Collin conductivity. This Collin conductivity that takes into account this whole balance can be very large. It can be about 20 times as big as the Hall conductivity, 10 to 20 times as big as the Hall conductivity. And this can give rise to huge currents flowing in regions where there's a lot of Hall conductivity and inhomogeneity exists. And so those factors give rise to all these different phenomena that I'll just illustrate for you. But these are the phenomena that define equatorial aeronomy. The dusk-dawn electric field, so-called superrotation, the pre-reversal enhancement, the fountain effect, et cetera, et cetera, et cetera. And I'll just go through these things quickly, and then I will at least put a name to everything that people like to talk about that's going on in equatorial aeronomy. These are plasma drifts measured at Hikomarka. Hikomarka is very good at measuring drifts, it turns out. And so these are vertical drifts as a function of time, and these are zonal drifts as a function of time, going over 4 or 5 days worth of data. So first of all, when you look at the vertical drifts, you see the ionosphere basically goes up, and then it goes down. It goes up, and it goes down. This diurnal behavior in the vertical drift is caused by the fact that we have different conductivity on the day side and the night side of the planet, and lower thermospheric winds blowing across those conductivity gradients give rise to a dusk-to-dawn electric field. The dusk-to-dawn electric field causes ascent during the day and descent during the night. It turns out right around the solar terminator, the evening terminator, there's a bump in the vertical drifts. They go up very rapidly, and then they fall. And this is called the pre-reversal enhancement. And it's very distinct at low latitudes, and some days more distinct than other days. And this is really just brought about because of conductivity gradients across the evening terminator, and both Pedersen conductivity and Hall conductivity gradients across the evening terminator. And it's just the dynamo process that I showed you before, and the fact that the plasma is acting like a dielectric. It's inhomogeneous. That's all you've got to know. The rest is essentially details. These are zonal drifts, east-west drifts, and what do we see? We see rapid eastward drifts at night and slower westward drifts during the day. These are just dynamo-driven drifts. During the day, the balance of the ionospheric conductivity is in the E region, so the plasma drifts with the lower thermospheric winds, which are westward during the day and relatively slow. At night, the balance of the conductivity is in the E region, the D region having recombined. So we have upper thermospheric winds driving rapid zonal eastward drifts. So we have slow westward drifts during the day, rapid eastward drifts during the night, and the whole ionosphere super rotates. Over the course of time, it has a net rotation that it's eastward. Something else that's interesting, it's a little bit hard to see, but there's lots of vertical structure in these drifts too, such that we have, at night, we have eastward drifts at higher altitudes and westward drifts at lower altitudes. This is brought about by inhomogeneity in the vertical direction, the fact that the conductivity increases with height, and that and the fact that we have dynamo winds blowing are enough to give rise to a shear flow, so that the flow is eastward at higher altitudes and westward at lower altitudes. So the drifts are very inhomogeneous because the conductivities are very inhomogeneous. This is some data from Koki Chow. This is something, a really new realization in Hikomarka. It turns out that these drifts that I'm showing you are incredibly sensitive to phenomena that are going on in the lower atmosphere. So it turns out that when so-called stratospheric warming events occur, when the polar vortex breaks up in the polar stratosphere, planetary wave activity causes a change in the way that the tides are blowing. The tides are pushing the thermosphere, the neutral thermosphere around. And through the dynamo processes that I talked about before, this telegraphs into huge variations in the drifts, the plasma drifts that are observed over Hikomarka in the upper atmosphere. So this blue line is sort of a climatological, what we would expect the vertical drifts to do over the course of a day. And these are vertical drifts that were actually measured after the onset of a sudden stratospheric warming event. This is maybe the clearest example I know of impacts that the lower atmosphere can have on the upper atmosphere. This is something we've been searching for in CEDAR for decades. And it turns out that it's sort of always been here. These perturbations in the vertical drifts that are seen over Hikomarka are tantamount to what you would see during a superstorm. And they're just caused by a stratospheric warming event, a fairly common meteorological phenomena. Another cause celeb of low latitude ionosphere is the so-called ionization anomaly, which is not an anomaly at all. It's very simple. The vertical drifts that occur during the day force ionization to go to higher and higher L shells. And if you look at this from above, you see that ionization therefore accumulates not at the dip equator, but in bands that are 15 to 20 degrees separated to the north or to the south of the dip equator. And again, not an anomaly at all. So I guess the anomaly is why we call it an anomaly. And something that Erhan Kudeki and colleagues at Illinois sort of discovered for the first time using Hikamarka data. This is a combination of coherent and incoherent scatter data. The green colors are electron densities. The red colors are coherent scatter from waves, and I'll talk about that in a minute. And the white lines are actually vector plasma drifts. And right around twilight, what we have is the formation of a nice vortex. And this occurs practically every day. And the vortex is a combination of two things. It's a combination of shear flow, so we have westward drifts below and eastward drifts above, and that's just coming about because we have vertical gradients in the conductivity. And we also have a reversed vertical drift, so we have ascent before twilight and descent after twilight with a little rapid uptick in ascent due to the pre-reversal enhancement. And we combine all these flow features together, you have a nice vortex. And it turns out that this vortex is itself destabilizing. And it's unique to the equatorial ionosphere. And then one last thing, this Collin current that I talked about before, that comes about from a Hall conductivity in the E layer that's very inhomogeneous, that's constrained to a very, very narrow layer, gives rise to the equatorial electrojet. So this is a very strong current system that flows. These are model results. This is a three-dimensional model that we have. And in this panel, what I'm showing is a function of dip latitude. So here's the dip equator. As a function of altitude, these contours are showing current density. And the current density can be enormous. The current density at midday on a standard, typical regular world day is several microvolts per square meter. And the vertical electric field here that's associating with it is tens of millivolts per meter. These are sort of auroral zone type electric fields and current densities, but they occur every day at the dip equator just because of the way of the conductivity, which is anisotropic and inhomogeneous. And this is a reliable feature. It occurs every day. It occurs every night, too. The direction is opposite, but there's not much conductivity at night. So when you actually measure, for instance, using magnetometers, measure what the total current is, it has this funny diurnal dependence. It's big during the day and vanishes at night. And so the ionosphere ends up acting like a big rectifier. So if we were to show electric fields here, we'd see that they just change direction between day and night, but because there's no conductivity at night, the current gets very small. You measure these things, by the way, having two magnetometers, put one right under the electric jet and one at somewhat higher latitude so it doesn't see the electric jet current, and then you difference them, and you're just left with a signature every day of what the electric jet is doing. And this is a great diagnostic of what the forcing terms in the ionosphere are doing, background electric fields mainly. I'm going to skip a few things here. So I keep saying over and over again, this impaired transport at low latitudes causes the ionosphere to be unstable. And indeed, that's what it does. Nature is going to demand that it gets back to some kind of an equilibrium configuration. And if you don't let it do so by normal transport, what it does is it becomes unstable, and it produces spontaneously waves. And some of these waves occur in the electrojet region. So I'm showing now coherent scatter from non-thermal irregularities, strong non-thermal irregularities in the electrojet region. These are daytime or going into evening or early evening echoes. These kinds of things occur practically every day. By the way, here's some meteor trails. We talked about this before. But these are electrojet irregularities. And we can make not just nice pictures of these things in Hikamarka. Hikamarka is very modular. It turns out that we can receive the backscattered signal in lots and lots of spatially dislocated modules, and then use sort of radio astronomical techniques to synthesize pictures, true images of what these irregularities look like overhead. And when you do that, you can actually see the plasma waves. So I want to show you what these plasma waves look like during the day and then at night. So here are the plasma waves during the day, and you can actually see them. They're color-coded, so the Doppler information is in color here. And if you look, you can actually see large-scale waves propagating with the direction of the electrons, opposite the direction of the current, from east to west. And the bands of red, blue, those are sort of kilometer-scale plasma waves. Actual, true, honest-to-God plasma waves. We're not inferring their presence. We can actually see their presence. So we can see them propagate. We can see them shear. We can see them being created and being destroyed. The wavelength is characteristically about 1 kilometer, like I said before. The drift speed is about half the drift speed of the electrons that are carrying the Hall current. So that's what they look like during the day. At night, they're still there. The currents are small. The conductivities are small, but the waves are still there. They're just going in the opposite direction. And it turns out that during the day, we have a nice smooth Chapman layer for ionization. At night, we have a nice raggedy layer. And what you have is waves that are trying to get going here, and they tunnel from one stratum to another, to another, to another. And so you get sort of these raggedy-looking waves that are propagating vertically as well as horizontally. These are meteors down here, by the way. And once again, we can actually see these waves. At night, it turns out the wavelength increases to about 5 kilometers. So we don't have to infer the presence of the waves. We can actually see them. They're large enough to be resolved from the ground. So we have lots and lots of movies like that. How does this particular instability work? This instability is called the gradient drift Farley-Buneman instability. I don't know what you'll be able to get out of this picture, but let me give it a try. I'm not a big fan of these kinds of pictures, but here we go. If we have a vertically stratified ionosphere, so the grayscales here are telling us what the conductivity is like. If you perturb it by pushing it up and down, then along any horizontal line, you now have built a wave into the conductivity. If you try and drive a current through that, you polarize it for reasons that I've talked about before. So these little black vectors here, dE, are perturbations to the electric field that was driving the initial background current. It's perturbed because the conductivity is perturbed, and this has to be perturbed to maintain charge neutrality. Now the electrons E cross B drift in the direction shown, and what that does is it has the effect of making the initial perturbation here bigger than it was before, and you have an instability. That's the gradient drift part of the instability. The Farley-Buneman part of it is this. This whole wave is moving very quickly with being carried by the rapidly drifting electrons. Ions that are sitting here watching this wave go by are going to feel a force due to their own inertia, and they're going to drift in the direction of these red arrows, it turns out. If the wave that's going by is going by sufficiently fast, the ions are actually going to drift in such a way that they drift into the density enhancements and out of the density rarefications. You have another instability, and that's the Farley-Buneman instability, and they work together, it turns out. And it's pretty easy to write down some fluid equations and figure out what the phase speeds and the growth rates of these waves are. And these equations, I'm not going to go into any detail. They're kind of useful. They kind of give you a few hints about the kinds of things that are going on, say, in the images that I showed you. But it turns out that it's a strongly nonlinear phenomenon. You really need initial value numerical simulations to figure out what's going on. But these tell you that the waves grow if the phase speeds are comparable to or larger than the ionacoustic speed. That's the Farley-Buneman wave part of the problem. And they grow if the vertical density gradient length scale is small enough that this growth term overpowers a recombination term. So you need steep gradients, and you need strong drifts. And if the drifts are really strong, that's good too. And these all produce plasma waves. The plasma waves primarily are propagating horizontally. So you may wonder why a vertically looking radar can see them. And they see them through mode coupling, through nonlinear mode coupling. So if you generate a horizontally propagating wave, it can essentially nonlinearly decay into 2 vertically propagating waves that the radar can see. Or 2 horizontally propagating waves can beat against one another and produce a vertically propagating wave. So nonlinear mode coupling allows the vertical looking radar to see these waves. I want to move on to the next kind of instability here, the so-called 150-kilometer echoes. If anybody has a better name for them, maybe that could be a CEDAR competition or something like that, a better name for the 150-kilometer echoes. Here's a picture of them. Here's, by the way, some nice summary data that Kudeki and his group and Koki Chow collected showing mesospheric echoes and the electrojet region and just incurrent scatter up here and the 150-kilometer zone in here. And so here are the 150-kilometer echoes. They have this interesting solar zenith angle dependence. They drop with altitude, reaching a minimum around midday. Lots of fine structure in here. Oh, and what's really interesting about this particular figure is it occurred during a solar flare. The solar flare was so strong that it caused absorption, so we couldn't even see the electrojet anymore. We couldn't even see the F region anymore. But despite all the absorption, nonetheless, the 150-kilometer echoes got much stronger, which is a pretty strong indication of what the source of free energy for the 150-kilometer waves is. And so I'll show you some data from Koki Chow and what our current thinking is. Let me go to the next figure. It turns out that one sees 150-kilometer echoes when one looks with the radar perpendicular to B. That's what these are. One also sees enhanced echoes when one looks off perpendicular to B. That's what these are. Looking off perpendicular to B, the enhanced echoes look just like ion line, look just like incurrent scatter, just stronger. Looking perpendicular to B, the echoes look like this. They have a very, very sharp part at very low frequency, at 0 frequency essentially, and then a broader tail. The broader tail looks just like incurrent scatter, looking perpendicular to B. So what these 150-kilometer echoes seem to be have 2 parts. A purely growing mode, essentially a 0 frequency part that you see when you look perpendicular to B. That's very much like what you see when you look at the electrojet or spread out for anything else. This 0 frequency electrostatic wave that's just sitting there telling you there are density irregularities around. And then this and this are telling us incurrent scatter. What we really have here is NEALs. We have naturally enhanced incurrent scatter occurring in the 150-kilometer zone when there's strong photoionization occurring. And we have this purely growing mode. And I think what we have here, sort of what our group is sort of deciding on is what we have here is a kind of an ionospheric modification experiment. So we have photoelectrons being produced very, very strong in a very narrow strata, and they're producing Langmuir waves, and they're producing Langmuir turbulence, strong Langmuir turbulence, and those are decaying into ionacoustic modes, which just look like strong in-current scatter and a purely growing mode. And the same kind of thing happens in ionospheric modification experiments when people pump radiation into the ionosphere with strong HF waves. So the theory for this is just sort of being worked out. I know Mirza-Oppenheim is looking at it, and Wes Swartz is looking at it, but that's kind of where we're headed. I think Koki has published those findings. The last thing I want to talk about, like I said, the real cause célèbre for equatorial aeronomy is equatorial spread F. And so here are some pictures, not from Hikamarka, but from a scanning radar in the Pacific that actually shows you a picture of what happens to the ionosphere when you really perturb it, when you really knock it out of equilibrium, when recombination comes along and wipes out the lower ionosphere, leaving a nice, heavy, dense F peak and F layer above it. And what happens is it goes unstable and it produces waves. And these are classic, heavy fluid on top of a light fluid type of wave. And this instability goes by various names. It's really the electrostatic generalized Rayleigh-Taylor instability, if you like. And what happens is regions of deeply depleted plasma from the bottom side break into the top side and carry these depleted plumes beneath them. This whole thing is field aligned, by the way. The whole thing is three-dimensional, that it's essentially uniform or close to uniform, or at least very elongated in the direction of the geomagnetic field. And what's the ionosphere doing? Well, it's trying to regain equilibrium by mixing. And it can't do it in a subtle way by vertical transport, so it's doing it in a violent way by just totally rearranging itself. And if, poor you're trying to communicate with radio signals, say with a satellite or with a GPS system or something like that, if you're trying to make some SAR imagery down here and your radio signals have to pass through all of this, you have a very, very strong diffraction screen here. And so you're going to experience diffraction and fading and scintillations, and things aren't going to work very well. And so Hikamarka sees these things too. When Hikamarka sees them, they drift overhead. Hikamarka doesn't scan. So we just get sort of a time history of what occurred overhead. And so we sort of see thin layers that break into these plumes and then some more thin layers. But we can do our radar imaging trick on this as well. And so I'll show you what these waves look like in radar imagery. And so those data are these data, only now you get a frame every couple of seconds or something like that. The lights are on a little bit bright, but you can sort of get the idea. Here are these big depletions that are passing through. Oh, thanks, Elizabeth. So here are pictures of the big depletions that are passing through. These are color-coded to contain Doppler information, but things are just very, very turbulent and very strongly mixed. And so here's a depletion, and here's one behind it, and here's one behind it. Actually, I think I know how to do it. Evidently, I don't know how to do it. OK. Yeah, so anyway, this is good grist for numerical simulations. Here, I'll do another one. Unfortunately, these figures are kind of enormous. So here's another event, and there's a certain sameness to these things after a while. So here's what the radar imagery shows. The resolution of these things is about 3 or 4 kilometers horizontally, and no, that's right, 400 meters horizontally and vertically. That's how good the resolution is. And the time resolution is about 2 or 3 seconds. And there's sort of a spectrum underlying every single picture in our image here, and the colors are trying to tell you about the moments of the spectrum. So here's a nice depleted region. You can see that things are evolving very, very quickly. It's not just sort of a stationary flow advecting in a sort of a frozen way through the radar volume. But anyway, so we have lots of accumulated movies. If you want to go to the Hikamarka website or to my website. If I were to draw a picture explaining how the Rayleigh-Taylor instability works, it would be the same picture as the gradient drift instability that I showed you before. Only now this is in the F region, so the electrons and the ions are both magnetized, and that's the only difference. But it's the same picture of what I showed you before. You produce some irregularities, they become polarized, they drift under the polarization electric fields, and the whole thing grows. And it's pretty easy to write down derive a linear growth rate for this instability, and it depends on the zonal electric field. So having a big zonal electric field is good, gravity is good, small collisions is good, and that means high layer height is good. The higher you can get the layers, the faster things are going to grow. And there's also, people usually put in a factor that looks like this, which is the ratio of the F region integrated conductivity to the total integrated conductivity on the flux tubes that are involved. And the idea here is that conductivity that's not in the F layer, that's say in the E layer, is just sort of shorting out the whole process, and that sort of kills things. So people have been, since time immemorial, using this expression to try to forecast, perhaps, whether spread F is going to occur or not on a given night by trying to calculate as many of these things as you can. Of course, it's difficult. We don't really know what the E-region integrated conductivity is. You can measure electric fields, but it's sort of difficult to know what some of these other terms are going to be. Also, this is a linear local growth rate, and one should really do things a little bit more carefully and do things in a non-local way. One should include the fact that there's shear flow, like I talked about before, which really complicates the calculation, it turns out. And then an overriding question is what gets this whole thing started. If you do some kind of a numerical simulation, you have to start with something and let it grow. And the question is, well, what do you start with? And many people think that, well, probably the thermospheric gravity waves get the whole process started and so forth. I'm sort of skeptical about a lot of these things. And lately, we've been doing some numerical simulations of spread F where we put all the physics in as well as we possibly can, including shear flow that occurs in the bottom side, including inhomogeneity and everything, including full three-dimensional effects, including the full solution to the 3D electrostatic potential. And it turns out when we do that, then over the course of an hour, which is I'm showing here, we can develop some pretty good facsimiles of these depleted plumes that are appearing in nature on more or less the right time scales, recovering more or less the right length scales, and more or less the right morphology. It turns out to get this to grow really quickly, we need to worry about not just the horizontal current driven by electric fields and gravity and so forth, but the vertical current that flows in here that's associated with the shear flow. If you have shear flow, if you have neutrals moving at a different speed than the plasma horizontally, associated with that is there has to be a vertical current to support that. And it turns out that vertical current is really destabilizing. In fact, it's more destabilizing in the initial stages of the instability than the traditional currents that people attribute Rayleigh-Taylor instabilities to. And to have a vertical current, you actually have to have some E-region loading. You have to have a dynamo that's not perfectly efficient. So that R factor that I showed you before, it should be less than 1. So in fact, we find in our simulations we get the most rapid growth when there is some finite E-region loading on the whole process, because it allows some parallel current to flow, and that allows vertical current to flow. And the vertical current is as or more destabilizing as the zonal current. So and no gravity waves needed to seed into this stuff. So I sort of have different emerging ideas about how this might be dealt with and how this might be forecast. Oh, one more thing. Spread F is a nighttime phenomenon. It occurs at night. Hikomarka occurs every other night, let's say. Sometimes it occurs during the day. Maybe once every 5 years. At least once every 5 years when we have the radar on, which is a real problem, because it's kind of hard to justify, running a radar at $1,000 an hour looking for something that occurs maybe once every 5 years. But here's some data from April. And these are incoherent scatter data. We were trying to measure temperature, density, and composition. And we're in a mode that was not suitable at all for studying ionospheric irregularities. But by pulling off some byproducts of our analysis. So here's some nighttime spread F. This is UT hours, so that means that sunrise is occurring around here someplace. And so the spread F goes away, and then we're doing all of our nice Aeronomy measurements, and everything's good, and everybody's happy. And then this is sort of late afternoon, and these incredibly strong irregularities appeared. This is during the day. This is daytime spread F, and it occurred after some geomagnetically disturbed conditions. As I said, this is very rare. We have 2 or 3 or 4 events of this accumulated for Hikomarka's entire lifetime. It's extremely difficult to know how you could possibly destabilize the daytime ionosphere. The daytime equatorial ionosphere is incredibly stable, and it's extremely hard to know what kind of situation might provoke something like this. There just seems to be no way to force it. It is very rare, but you'd think it would be entirely rare, like would never occur, but it does occur from time to time. By the way, Odile, there's Odile. CNOPS was right here.
I know, I'm writing the time.
Okay, well, no, I already talked to Patrick. CNOPS was right here. It was right over Hikomarka. It was at perigee. It flew right around here. Sorry, it wasn't at perigee. It was near apogee. It flew right through here, and it saw absolutely nothing. So thanks a lot. But it saw absolutely nothing. It's very interesting. So what could be better? We had the radar on and CNOPS right there during one of these very rare daytime spread F events, and who knows? So another frontier for Elizabeth. Anybody who wants to work on the daytime spread F problem is welcome to do it. So rather than writing down conclusions, I don't really have any conclusions other than that this is a very rich area of research, a very rich field to pursue research. Instead, I just wrote down the names of people that I stole material from. And the conclusion is there's lots of work to be done here, and maybe you can keep an eye out for some of the things that I talked about during the course of the rest of the meeting. So thank you very much.